Okay, class. So here we are for the third assignment. Third piece of our summer assignment, taking a look at some questions here and how to work some problems around forces. So just to give a quick introduction of Newton's laws briefly, there are three laws of Newton's laws of motion that we've probably studied in the past in some physics course, if you had it with me or not. And the first law is usually called the law of inertia, and this tells us that an object at rest stays at rest, an object in motion stays in motion unless acted on by an outside force, an unbalanced force, something like that, an external force. When this law describes the word motion here, it's talking about motion at a constant velocity in a straight line, okay? All right. So this is Newton's first law, law of inertia. We're at rest, we stay at rest. For motion, we stay in motion at a constant speed in a straight line unless acted on by a force. The second law tells us about that force. It tells us the force is going to change our motion. So we have an acceleration, that's our change in our motion, and it's going to equal whatever the sum or the net of all the forces is divided by the mass. So this kind of relationship here says that if this term, mass, in the denominator is small, then you divide by a small answer, you get divide by a small mass, you get a big answer for the acceleration, the change of motion. Okay, so this term here describes our change in motion. Do we change a little or change a lot? Okay, this is your resistance to the change in motion, right? This is our mass, our inertia. So the inertia fits in right there in the equation, because mass is a measurement typically of the inertia of an object. That is not a definition of mass, but it's how it operates in this formula. Lastly is this net force that we have in the numerator of this equation, and this net force is kind of our overall push or pull. Okay, after all the pushes and pulls have subtracted and added, we're left with this little push or pull right here in the numerator. And those are our three terms. This equation is also sometimes written a little differently. It's sometimes written as the sum of the forces, or the net external force on a system, which we'll get to the word system shortly, is equal to MA. That's often how it's written. As we study through the year, we will also look at some other situations where not only our motion's changing, but our mass can change as well. So we'll look at a different way of writing Newton's second law, and we'll look at it as a product rule, okay? But that is not for today or for the summer homework. That is beyond the scope of what we're doing for the summer homework. So this is the basic little piece of Newton's law. One of the things we're going to see, we've seen before, earlier, is we're going to see some triangles with trig and such. So just to teach one or two things before we get there. Again, if we have an angle theta here, this is called the hypotenuse. This side is adjacent or next to the angle, but not the hypotenuse, the longest side. And this is the opposite side. This is going to be a right triangle. And we use this right triangle geometry because it fits a lot of our problems that are on x and y axes, where y we're calling the vertical axis, x we're calling the horizontal, and they're also at a right angle. So since we often decompose or break up some vector quantity into components on an x and y axis, this right triangle geometry right here is really helpful for us. And if I want to find out what this opposite side equals, I could use the sine function. I'm moving very quickly here because, again, we've covered all this previously. We're just doing it very quickly again. If I multiply both sides of the equation by h, the hypotenuse, then I could get that the hypotenuse times sine theta equals the length of the opposite side. Over here for adjacent, I could use my cosine function, and I could say cosine theta equals the length of the adjacent side over length of the hypotenuse. If I rearrange that, I can say h, the hypotenuse, times the cosine of the angle equals the adjacent side. We're going to use this idea quite a bit, and one area specifically is to break up our weight vector into components, okay? So I'm going to teach that skill here quickly, and then we'll jump back and actually work some problems. So here is an inclined plane. And on our inclined plane, we shall put a box, right, of mass m. And this box of mass m is going to be sitting perfectly still. Friction is going to hold it in place. And we might want to find the value of the friction, and we might want to find the value of how much the surface is holding up the object, or sometimes called the normal force or perpendicular surface force we use in class. And those are all synonyms. And we're going to look at that more clearly here in just a moment. I'll do lines, arrows, red's fine. So this is going to be my weight vector. And let's make that line a little heavier. That's too much, isn't it? It's a little better. And so that's going to be my weight vector. And to review what I mean when I say weight very briefly, we're going to use our F equals ma formulation, and we're only looking at one acceleration. And it's going to be the acceleration that is due to gravity, which we have a special symbol for 9.8 meters per second squared, the acceleration due to gravity. So if that is my acceleration, then the force that I'm discussing is the weight. And by weight, I'm just talking about how much gravity is pulling you toward the center of the earth or making you want to fall toward the center of the earth, okay? You may not feel that pull so much if you're just sitting in a chair, because the chair supports you in the same way the inclined plane is currently supporting our mass in this problem. So I'm going to put a little red W here next to this red arrow. And I want to break or decompose that weight vector up into two different pieces, two different coordinate pieces here. And I'm going to put a coordinate system on this problem. And the coordinate system is going to be turned. It's going to be inclined, just like my plane. And that's going to be an advantage if this block was sliding up or down the hill. So I'm going to call this my x-axis and call this my y-axis. And I'm going to find out how much this W vector projects itself onto the x and y axis. All right, so if I look, there is some length right here that the W vector kind of makes a shadow or projects itself onto the y axis. And there's also one for the x-axis, like this. And I can take those two together, and if I take that one up top and redraw it here, it makes a right triangle, okay? Or if I take the projection I drew first on the y-axis, and I draw it starting at the tip of this other arrow here on the x-axis, then it also, I'm not in the pen mode, it also draws a right triangle. The two right triangles together, you can see, make a rectangle there. And so I want to decompose that or break it up. And so let me actually get rid of some of those arrows and clean it up again a little bit. Okay. And I'm going to magnify that or draw a much bigger version of that over here to the side so I can work on it. Okay, so here is my W vector going straight down, and I want to decompose that or break it up into two pieces so that it's in a right triangle. I'm going to call the one that is perpendicular to the hill on the y-axis W perpendicular. I'm going to call the one that's parallel to the hill W parallel. Again, those are just variables. They're not that important. All right, so here's my triangle. And I look at it and I wonder, I'm like, but I don't know the angles here yet. So I want us to do a quick little geometry lesson. And you can just follow here with your eyes, and hopefully it will all make sense. If this is the angle of the hill right here, I want to observe that my black marker I used to draw the hill has a 90-degree angle, this little blue angle here, and this angle must be complementary to the other blue one. So I must be looking at 90 minus theta, since it's 180 degrees in a whole triangle. All right, so here is 90 to the 180, and the other two angles also equal 90. But I can see with this red arrow going straight down to the center of the Earth, since Earth causes gravity, that this angle of 90 minus theta must also be the same as this. That must be 90 minus theta. Okay, just kind of absorb that for a minute, because my red arrow down is parallel to this black marker side of my hill. And these purple dotted lines that form my coordinate system of X and Y, they're obviously at 90-degree angles. And so if this one is 90 minus theta that I've marked, then this little angle right in here, that must be a theta, because those two are complementary and they form a right angle. Okay, so the dotted line again coming down and the hill make a right angle. And so if one of them is 90 minus theta, that one's theta. Here's why that's important. Because in our red triangle we drew off here a moment ago, I now know that this angle up at the top is the same angle as the hill itself. So we're going to see in our homework set we're going to look at, we will often be given the angle of the hill. And we can break up the weight vector into two pieces, two components, to see how much of it is parallel to the hill and how much is perpendicular. We care about that because only the parallel part right here, that's the only part making us actually want to slide down the hill at all. So when we're using it, we'll often use that piece of the puzzle. And the perpendicular part will be used for saying how much we push on the hill. And that's important for things like friction, because the harder you push on a surface, the more friction there is. Okay, so let's go ahead and find those two little pieces, weight parallel and weight perpendicular. You may just see, obviously, that weight parallel right here is opposite my angle. Okay, so if I come back and look at my trig review I did, the opposite side I use sine. The adjacent side I use cosine. So to find weight parallel, I'm going to use sine. To find weight perpendicular, I'm going to use cosine. All right, so we can just kind of write those out now because we know what they are. So here is weight parallel. It's going to be the W times sine theta. And right above here, I have written down what W is. Right? W is mg. So we often write it like this. Mass times 9.8 meters per second squared times sine of the angle of the hill. That's how much of the angles, sorry, how much of the weight of the object is pointing down the hill. To find the other weight perpendicular, it's the adjacent one, so we use cosine. And I'll say the whole weight, the hypotenuse, times cosine of the angle. And that's going to be the amount that the block is pushing down on the hill. Sometimes we write that. Instead of a W, we'll use the mg if we're given the mass, since the G 9.8 is a constant, doesn't change. And we'll write it like this. Okay, so that's a strategy we're going to use in a lot of the problems. So let's just look at what we looked at so far and review it just for a moment, and then we'll go on and review one or two more new ideas. First idea here is law of inertia. Object at rest remains at rest. Inertia is often a measurement of the mass of an object if we're looking at things moving in a straight line and treating the whole block like it's a little tiny dot or a particle. We just say the inertia is the mass. Newton's second law discusses the relationship here between these three things, the acceleration and the mass and the force, and shows us how those three are related. The force here is a net external force on our stuff that we're looking at in the problem that we often call our system. So we can rewrite that equation over here and say F equals ma, okay, which is a more common version you've seen in class, I'm sure, regardless of what physics class you were in. Oops. And then we can also consider our trigonometry here, where we are looking at sine and cosine to find the length of the sides of the opposite and adjacent. And the key reason we care about that is because we're going to use that as a strategy in our hill problems, where we're breaking up the weight vector into components of parallel and perpendicular. Okay, let's quick review. One more thing I want to just review and throw out that we will be using quite a bit is the idea of friction. Okay, friction has two different things, and I write the little cursive F because that's often how we write the force of friction. That's a symbol we usually use. So friction has two different things that affect it. Okay, one is the surface. How smooth or how sticky is my surface? And the other is how much we push into the surface. And those are the two parameters that affect friction. Again, if you've had an introductory physics course, you've probably done that stuff. We'll do some labs in my class where we'll pull some blocks along with force probes and such, and we will discover some things about friction that we're writing down here in words right now if you haven't done it before. So the equation that we write for this is we write F, That means friction. And the surface is given a symbol like this. It's like a U with tails on it. So it's a Greek letter mu, and it's like a little U with tails on it, and it's called the coefficient of friction. Okay, so coefficient just means number. If you remember that from chemistry, you put coefficients in front of molecules when balancing chemical equations. So the word coefficient, okay, just means number. All right, and then we have our push into the surface, which is our normal reaction force or perpendicular surface force. I'm going to write that for the moment as a capital F with a subscript N. So for the problem we just worked, it would be our weight parallel. The weight parallel shows how much we are pushing on the surface for our little mass right here. Oops. So this little block right here, this mass, is pushing on the surface, not with all of its W, with just the W perpendicular. And that's why we care about finding the W perpendicular in that problem, because it's going to be useful for friction down here. All right, so that symbol will be used. I do also want to note that there's two different kinds of friction. We have static and we have kinetic. So static, think of static cling, it means still. Kinetic, think of moving like kinetic energy. Okay, and what this is saying, you probably have the experience in your life if you moved a heavy piece of furniture or anything like that, a washer or a dryer or something. It's harder to get it moving sometimes. It feels like it's kind of stuck to the floor than it is to keep it moving. Even just a heavy box full of books or paper, if you're shoving across a carpet or a floor, even if it's only been sitting still for a minute, it's harder to get it moving. And once it's sliding, it's easier to keep it sliding. So static is the still friction, and kinetic is the sliding or the moving friction. And they're two different numbers. And where they actually differ is they differ in our coefficient of friction. So for a single surface, say a box on a carpet, you would have one number that's a coefficient of friction if it's sitting still. Maybe be rated at like a 0.7 of friction. And if it's sliding, maybe it's only a 0.4 of friction. So the friction gets less when it's sliding along. And there's a lot of chemistry and physics that goes into that, and the two surfaces and what's happening at the level of the electrons and how much air is between the surfaces. And there's a lot that goes into friction, and some of it is very easy to understand, and some of it is very non-linear and turbulent, and we're not necessarily going to spend a lot of time mathematically analyzing or modeling some of those things, but we can slowly discuss them conceptually when we get there in class. Now let's actually dive into the assignment, okay? I think we have our pieces we need to dive in and work some problems. So number one we'll look at here, we have a block that lies on a frictionless surface. Frictionless is really important because that means we can just totally ignore the coefficients of friction, the normal forces. We don't care about these things. And the block is connected to a cord passing over a pulley. So we have two different blocks, and they have two different masses. Okay, we have 6.67 and we have 6.83. And it asks us to figure out what is the acceleration of the first block. Okay, turns out if we find the acceleration of either one of these, we're going to find the acceleration of both because they're attached by a rope and the rope's not moving around. So if you pull one block, the other block moves with it. So these two blocks will move together as a single system. All right. So let's go ahead and take a look at this problem. And let me see, there's a part two. There's a part two. It usually asks for tension in the cord. Let's see how F equals ma will help us solve this. So one more skill we want to add to our little bag of tricks right here is to be able to draw a free body diagram, okay, or a force diagram sometimes called. So there are two blocks. Here is the block that is on top of the table. I'm not going to draw the table. I'm not going to draw the pulley or the string. I'm just going to draw the block on top of the table. And now I'm going to draw some arrows, and I'm going to start all the arrows from the middle. You don't have to do this. I like to do this. I'm going to use F with a subscript G for the gravitational force. I could use a capital W as I did in the previous example. Some people use a W, some people use F with a capital G, some people just write MG right here. All those notations are just fine. The table is supporting this block. It's not letting it fall. So the table must be pushing up with the same force to balance it out so that it doesn't accelerate downward. And so I'm going to put, like I do from geometry, little tick marks on these two, showing that they are congruent in length. Not the same direction, not the same vector, but they're congruent in their length. So however much gravity makes it want to fall, that's how much the table holds it up. If gravity was too strong, then the table would break. There's also a third force, and it's going this way. I'm going to put an F and a subscript T. So all these have a capital F, that means it's a force. And they all have different subscripts, and those subscripts are describing for me the interaction between two objects. So the first force I put down is G, so that's an interaction between the block and the earth, because that's what causes gravity. The second one has an N. That's the interaction between the block and the table that causes my normal force. The third one's a T. That's an interaction between the block and the rope or the string, and that tension causes a tension force to the right. And so again, I put a capital F for forces, and I just change out the subscripts to communicate what kind of force it is and what kind of interaction we're looking at in that situation. That is the free body diagram for the block that is on the table. If you haven't done free body diagrams in years, just catch up. Let's dust off those cobwebs and try and remember a little bit. We'll spend more time in class going through very detailed procedures for doing free body diagrams, but for today, as with everything else in the summer assignment, we're just kind of moving quickly. And here, I'm going to draw an FG going down, and I'm going to draw an FT going up like this. And I'm going to be very careful to say these two are not equal. In fact, I'm going to redraw this downward arrow to be just a bit longer to emphasize this. I know they're not equal because my system is accelerating. And the reason the system is accelerating in this case is because this arrow is longer. It's longer than the arrow going up. So when these two kind of fight it out, like a tug of war, and if I subtract their magnitudes, that is the size of the number of them, how much the arrow going down is and the arrow going up, if I subtract those two numbers, I will not get a 0. So I won't put these tick marks right here, that I have on the other example. No tick marks because they're not congruent because the system is accelerating. All right. There is one other thing I do want to mark congruent, and that is that the tension, I'll put 2 tick marks, is the same tension here. We won't always have that luxury in every problem here, but with our magic frictionless pulleys of physics that have no mass that we're using in this problem, that means that our pulley only changes the direction of our force. And since the rope is the tension, whatever the tension pulls on one object, it pulls on another object. That may not be obvious to you at all, but we'll do some labs and examples in class where we're going to show that. Okay, let me review quickly what I'm talking about.
Oh, I like this arrangement.
All right, so here in this problem, again, we are just looking to see where it talks about the pulley, and it makes some statements that it does in a lot of these problems that we can simplify our problem, make some little assumptions about the problem. And so specifically here it says, assume that the cord is light. Okay, so it's massless or weightless, so we don't have to worry about the cord itself adding weight to the problem. It's unstretchable. That means they're both going to have the same acceleration. If one moves, the other moves. And it talks about our pulley. The pulley has no friction, and the pulley has no inertia, no rotational inertia. So it doesn't have mass, it doesn't have friction. It's not going to slow us down. All right. So let's go ahead and now finish solving this problem. I'm going to work this 2 ways quickly with different systems, and then we can kind of appreciate why one is a little bit better than the other. First, let's just look at this situation right here, okay? Just the block that's descending. I want to consider this a friction, and I'll write down an F equals ma problem for it. So I'll jot down my equation first, like this. I see there's 2 forces. That is, I have 2 arrows. And as I look at my 2 arrows, 1, 2, those are my 2 terms, Fg and Ft, that better end up in my equation. I'm going to choose the downward direction to be positive, not because it has to be, but because that's the direction my block's accelerating, okay? That's convenient for me. So I'm going to say that these 2 are going to subtract from each other. That's subtraction signs because one's down, one's up. If they were both down, I'd add. okay, because they'd be in the same direction. Again, this is a tug of war. So the tug of war means they're going to be kind of canceling out each other's forces, and the mathematical way we show that is subtracting. So I have an equation down. Okay, that equation is for the system in that box. Let's go ahead and do another equation in red for this red box. Let's do one for this system. Now, these two forces, Fg and Fn, that are vertical, I'm not going to put in my equation. I'm not going to put them in my equation because they're not causing acceleration. I'm also not going to put them in my equation because they're not in the direction of the acceleration. This acceleration right here is to the right, right? And so I only want to put in the forces that are to the right. So in this case, it's just Ft. Now, when I look at these two equations, I have to note that they are not kind of set up and finished. They each have two unknowns. I have an Ft and an Ft. That's an unknown. And I also, have an A and an A. So I have two equations and two unknowns. I can substitute and solve. Okay, and you could do that, and you would get the answer for both the A and the Ft, and those are the two things we're looking for. There's another way to do the problem. The other way to do the problem is I can do a system that covers all of them, like this. Notice the system now encompasses both boxes and all the forces. And so I can consider that my pulley is just changing the direction of the force, and that this Ft is really in the same direction as Fg. That is, it's making everything in the system accelerate. Right? And so let me draw here in blue and say sum of my forces equals ma. And this time I'm going to list three forces because there are three forces in the direction of motion. There's my gravitational force on the block that's descending, right? This one here, minus the tension force pulling up on the descending block, making it not want to go as fast. And then I'm going to add in the tension force that is pulling the other block sideways. Now, you might have noticed right away, I have a plus Ft and minus Ft. Those two are going to cancel out. And the reason they cancel out is because they're what's called internal forces now. My big blue block has circled both blocks in the system, and the tension force is the two blocks interacting via the string of the rope, pulling up on one or pulling sideways on the other. So it's an internal force in my system. And I mentioned earlier, way up here in the beginning, that when we write down Newton's second law, these are the net forces, or the external forces. And this net external force right here does not include the internal forces. So by choosing my system just a little bit differently, as I did down here, I've strategically kind of canceled out my two frictions. Okay? Let me put in MA, and I'm going to rewrite this. Instead of FG, if it's all right, I'm going to put M. And I need to remember which M this is. There's two M's, and they're 6.83 is the mass that hangs, okay? So that's my 6.83 mass right there. I'm going to call that mass 2, all right? And over here, this mass, I have to be careful. This mass is not the mass of M1, the block on the table. It's not the mass of M2 that's hanging. This is actually how much inertia the whole system resists the acceleration with. So there's actually two masses here that both have to pick up speed. And you're going to have to get both M1 and M2 going. And you only have one force to do it, right? Because our tension's canceled out. There's one F left. So this one F has to get both masses moving. So the M in this equation is not a single mass this time. It's the mass of my whole system. Here it's M1 plus M2. Okay? Now, you might say, hey, this equation looks much nicer because I look at it and I got one unknown. That's it. I can solve this right away. It doesn't give you tension. Not this equation because I canceled all the tensions out. But it does give us the A right away. So it's two different ways to work the same problem. One is not correct, the other one's wrong. They're just kind of different ways of looking at the problem, whether you want to look at one big system or two smaller systems. Let's go ahead and actually solve this equation right here. So I'm going to plug in my two M's and get some numbers and solve this. Okay, so I have plugged in some numbers here for the mass 2 and the gravity on the left of the equal sign. Added up my masses on the right of the equal sign. When I multiplied together the mass and the acceleration, okay, I found a total force of 66.9. The units here are in newtons. And that's just the unit we use on forces when we're using our metric system with meters and seconds and kilograms. So that's not a magic thing. That N means that I multiply to kg times an M divided by an S squared. And we put N just to simplify all that writing. Divided it by the mass here on the right-hand side. Because it's multiplied times A, so I divided it over. I got 4.96 meters per second squared as my final acceleration for the problem. Okay, so that is how we work that first little one. I want to jump into a little more awkward or a little more challenging problem here, and so we will do that. Let's look at number 13 because it's pretty complicated. Okay, in fact, it's not the most complicated, perhaps. Maybe it is, but that's a good one to do work. Okay, so the suspended 2.7 kilogram mass on the right is moving up. Okay, so that's over here. We have a mass, and this mass is ascending or going upward. And if it's accelerating upward, right, then that means that the tension pulling up must be actually more than the weight. So that means our mass over here, 8.8, must be moving downward. And so the weight downward applied by the Earth must be more than the tension upward trying to prevent it. Here on the hill, we have a block, and this block is going to have its own mass. And part of that weight vector acting on this block will be parallel to the hill, and we'll have to look at that. But look here, we have friction this time. So we're going to calculate, using that coefficient of friction, something about a frictional force acting on it as well. So the friction is resisting the motion. So friction, again, just to define that, is a force that resists that relative motion between those two surfaces. And since this block is actually moving this way with a certain velocity, I know my friction is pointing opposite that motion. I'm going to put an F there, back off to the right or up the hill. And so I want to look at this problem because it's pretty complicated. And I think if you can do this, you can do any of them. First off, they want to find the acceleration of the whole system. Then they want to know what the tension is connected to the block on the right. Then lastly, what is the tension connected to the block on the left? Okay, this is pretty complicated. First thing I want to do here to make my life just a little bit simpler is I want to redraw. And I want to redraw the whole system. I'm going to show you a way that for some people really helps them to redraw the system. So we're going to redraw the system almost more like a straight line. All right, so here is my block on the left. This is the big heavy block, the 8.8 if I recall. And it has a force of gravity and it has a force of tension. And gravity, if you remember, is bigger than tension, so I probably should have given the arrow a little more length to demonstrate it was a bigger force. Then there's my block on the hill. Man, this one's complicated. So this one has gravity going straight down. It goes straight down because the Earth is straight down beneath it. We don't look at the angle of the table when we draw the force of gravity vector. Then there's a table, and the table's supporting just part of the weight, like this. Okay? Then there's also friction slowing it down. All right? These arrows may not be drawn to scale. That is, that my friction arrow probably is not as much as my force normal arrow, or perpendicular surface force, the one that is right here. Right, that is bigger than force of friction, but I just drew them the length that I did just for demonstration purposes. There's also tensions in here. So let me think about my two ropes. There's one rope that is pulling this block. Man, that's pulling it down the hill. I'm going to call that T1. We'll call it T1 over here. That's the rope between the block on the hill and the block that is descending. There's another rope. There's another rope going up the hill this way. We'll call that FT2. All right, and that is the rope that is connected to my 2.7 kilogram block over here. So the 2.7 kilogram block has its own FG, and it has another FT. And these two tensions, T1 and T2, they are not equal. If we think about it for a moment, and I'll go back to the picture, the tension on the left-hand side actually has to get two blocks moving. So my rope right here, that rope has to get the 1.8 and the 2.7 accelerated. It's like if you had two friends and you grabbed the hand of one friend and they reached out and grabbed another friend. If you pulled both of your friends, you'd have to pull hard enough to get both of them moving. If you look at the other rope, the rope over here, this rope only has to pull hard enough to get the 2.7 kilogram block moving. So it doesn't have as much mass resisting it. It doesn't have as much inertia to overcome. And so it's not going to have as much tension in order to get the same kind of acceleration. All right, so the two tensions are not the same. One of them pulls 2 blocks, one of them pulls 1. You'll see in another question in your homework, you'll see a similar kind of situation. Here with the 6.9, you have an F, and that F has to pull all the blocks. That's not true for T1 and T2, and I'll let you work on that more when you get there. So here's my force diagrams or free body diagrams in my system. And if you have to go back and listen again to what I did for the middle one, listen to it again. It's pretty complicated. And when I write down F equals ma and I figure out, hey, which of these forces actually govern motion? This Fn that I highlighted yellow is the only force that does not have anything to do with my motion. Okay, this tension, that makes it want to go faster. The weight, that makes it want to go faster. This is helping it slide downhill. The tension and the friction, those two are slowing it down. All 4 of them need to be in my F equals ma equation because all 4 of them, either the whole force or in the case of my gravity, part of the force, is going to be working in the direction of the acceleration. Okay. I'm going to go ahead and just write down one big long F equals ma equation here. And if you again need to pause and look at this and think about it for 5 minutes, that is totally all right. This F is going to be the net force on the whole system. I'm going to circle my system like so. Okay. And so I'm going to have all 3 of them be the system. That means that when I fill in the mass on the right-hand side right here, I better have all 3 masses in there because I have the whole thing in a system. I'm doing this because I don't want to have just one unknown in my equation, just my acceleration. Okay. So first I'm going to use terms with no numbers. And let me even add a 1 and a 2 to my gravities and a 3 to the one on the hill, just so that I can denote when I put down FG in my equation, which FG I mean. So I'm going to put FG of the first block minus force tension 1. That's this term right here because it's pulling up, so I give it a minus. I give this one a plus again because it's in the direction that the whole thing's accelerating. Then I'm going to start to look at the block on a hill. The block on a hill will have 2 different forces, force tension 1 and force gravity 3, that are going to be positive. And then it'll have 2 here that are negative. Okay. So plus force tension 1. I'm going to note right away those cancel out. They're an internal force. Plus force gravity 3. Now watch this. Sine of the angle theta of the hill in the problem. That again is to take only part of the force of gravity because we're on a hill, so only part of it, the weight parallel, or using the sine theta to find that component that's parallel to the hill. That's all we're using. Now let's put in the 2 that are subtracting. I have my force of friction that subtracts. That's a capital F with a cursive subscript F that I chose to use here, but it's just a variable. You can use whatever variable you like. And then I'm going to put in force of tension 2, is pulling uphill. Now we come to our last mass. This first term, force of tension 2 right here, that's in the direction of the acceleration. It's positive. This gravity in this case is pointing against the motion, against the acceleration, and it is going to be negative. So I'm going to add FT2. Note they cancel out right away. They're internal forces. And sorry, I put a plus there almost, minus FG2. And all of this equals, I'm going to write it above because I'm running out of space, M1 plus M2 plus M3A. Now that's a long equation, but watch how it kind of slips down and simplifies pretty fast. I'm not going to write all my terms I canceled out in the next line. So I'm going to say mass 1 times G. That's my F1G term right there. Okay. Next term I'm going to write is this FG, 3 sine theta, M3G sine theta. Next term I'm going to write is my friction term. And please remember the friction term. If you remember the formula we had up above, it's a mu times a force normal. So I'm going to put in mu. That's the mu. And then I'll leave it force normal for the moment, but we're going to see in a moment that it's part of the weight of mass 3 that's sitting on the hill, and we'll see that in just a moment. Oops, this is supposed to be m2g over here on the end, and all this equals m1 plus m2 plus m3a. We're almost there. Every single thing I've written down is a given number except this fn. I know what m1 and m2 and here's m2 and m3 are. I know what the g is. I know what the theta is. The mu was given as 0.12. All these are given numbers except the a and the fn. So let's go back and look at my picture one more time and take a look at my fn. My fn right here, if you remember again, we said is part of the weight. So let's go all the way back to our top example, and we see that this weight parallel right here, that's equal and opposite to my perpendicular surface force or normal force. Again, those are synonyms. Okay, so those two are congruent to each other in length because one of them balances out the other. So the normal force is pushing up off the hill this way, the force normal. It is balancing out the weight perpendicular, the part of the weight that pushes into the hill. All right, so here's the equation for it, mg cosine theta that we saw earlier. I'm going to pull that down here and use it. So I'm also going to factor out my g's from all these things because they all have, well, maybe I'll leave them in there. I'm going too many math steps at once. Okay. Here's the mu, and this is m3g cosine theta minus m2g equals the megamass of all three of them added together, okay, times A. Every single thing here is a number that is given except for A. So you can find A right away. As far as finding your two tensions on the side, you can use just these free body diagrams, these force diagrams. This one, once you know A, will right away give you the tension on the left-hand side here, which I called FT1. And so my system, again, is just the blue box that I circled there. And then I can have just this little green box over here that I circle. And that's my system. And once I know A, I can just write down this really quick little equation here. And I can say for this little box right here, that force of tension 2, that's positive, minus force of gravity 2 is equal to just m2a. So A is going to be found from the equation we have below. So that's going to be known. Force of gravity 2 is just m2 times g. And I do want to note this is just m2 right here, just m2, because look at my green circle. My green circle only has one mass in the box. It only has two forces in the box, this one and this one. So I have two terms, 1, 2, on the left-hand side for the forces, and just one mass in my system. And again, A is known. So the tension right here is found, class, by doing m2a plus m2g, and that gives it to you. Same on the left, we'll give you the blue one, okay? And we'll come back and finish this in just a few minutes. Okay, so taking a look here, again, at this problem, we're working to calculate numerically A. We're just going to plug in the numbers. And so 8.8 is the number of kilograms for mass 1, 9.8 is the G, and so on. We plug in all the numbers from the given information in the problem. Notice here I have divided by 8.8 plus 1.8 plus 2.7. That's our megamass of mass 1 plus mass 2 plus mass 3. As a quantity, they're multiplied times A, so I divided both sides by the three of them so that we can get A by itself. All right. As we plug those numbers in, what I got here on a calculator was 63.22 for the numerator on top, and that's in mass times acceleration, or kilograms times meters per second squared. The denominator is just the three masses added together, 13.3 kilograms. Okay, our units of kilograms cancel out. And our acceleration I got was 4.75 meters per second squared. So having that A from using the F equals ma for the whole system, all three masses, we now can again look at this little green and blue circle and plug that A back right in to here, and that would give us for the tension on for this little green, using the green circle, we can get the tension on the right hand side for the 2.7 kilogram mass. And we'll plug in the numbers here and get that for the two tensions and make sure we understand what they are as well. So we calculate those two tensions with our acceleration of 4.75 meters per second squared. I kind of rewrote the equation down here for the block on the right. Then we have tension minus weight, and tension minus weight. There we go. So the tension minus the weight equals the just mass 2 times acceleration. Again, we only have mass 2 here because that is the system when we look at just the one mass. And we move the mg to the other side by adding it, plug in the numbers here down below for the mass times A and the mass times gravity. And I got a little less than 40 newtons for the tension in the string on the right. For the one on the left, if we remember, there was two forces, and the force of gravity was the bigger one. All right, and the force of tension I'll make negative because that was the force that was opposing it. Gravity was in the direction of acceleration, which I'm calling positive for this problem. And here I'll put in m1 times A. So we get m1g minus F tension equals m1A. Solving for tension, we're going to get m1g minus m1A is equal to that force of tension. We plug in numbers here. Let me go back and remember, 8.8 was our mass. And 4.75 is our acceleration. I'm running out of room here a little bit. Okay. And let's see what that equals. I think 44.4. Okay, newtons. And just to make a note here, that the tension on the left-hand side is greater, okay? It is a larger number, and we kind of expect this number to be larger than the one on the right, because if you remember again, we said the one on the left has to get 2 blocks accelerating, 2 blocks moving. Let's just go back to the diagram on the problem itself. So there are 2 blocks here to get moving. So we said this tension here has to be greater to make both the 1.8 and the 2.7 accelerate, as opposed to just the 2.7 accelerating with the tension on the right. And there, I think it's worth making one more note about the system that we chose and the masses that we chose. So again, when we circle here in blue, then the only mass is mass 1 of that system, because I'm only looking at the 2 forces acting on just that one mass. That's the final thing we just did. The other shorter equation we did here is in this green circle, and we considered just the 2 forces on this mass and only use that mass in the system. So the formula F equals ma that we have right here, it applies to the system. The system could be 1 mass, it could be 2 masses, it could be 3 masses, but the F, the sum of all the external forces, has to apply to however many pieces you have in the system, and also the mass becomes the mass of the whole system, and the A is the acceleration of the whole system. In order for that to be true, we can say explicitly here that the masses all have to have the same acceleration. They have to be attached in some rigid way. We're considering all these blocks to be little tiny point particles. We're not considering them to have shape. We're not considering if the blocks could tip or spin. We're not considering more complicated motion like rotation and that sort of thing. We will consider those things later in the year. but not at this point. Also, we're not considering the pulleys to have any kind of friction. We're not considering the pulleys to have any kind of inertia that you would have to cause them to turn. And so that is something else also worth mentioning. One more thing I want to mention here, and then we'll kind of close. Many people like to visualize a problem like this, where they have pulleys. And in our little problem, we have 3 blocks, right? And I'm not going to draw the pulleys for the moment, kind of just the strings. So they kind of like to imagine this kind of problem, and they kind of straighten it out. So they take this one and move it that way, and take this one and move it that way. And the purpose in this is to kind of see that it's one direction. Because what I want you to make sure you understand is that everything is accelerating in this direction. So I chose to call every force that's in the direction of that yellow arrow positive, and every force against it negative. The reason some people like to move the masses and instead draw the system like this is that they can now see which ones are left and right, and much more clearly identify things that are going to be positive or negative. So here we had gravity down, okay? So this person working the problem this way would put gravity to the left. And the tension going up on this block, they'd put the tension going this way. Okay, that's what they'd put tension 1. And then the tension 1 that works on this block and the weight parallel, they'd put that way, and so forth. Okay, we have, we said a force of friction, and also there's a tension to the back. So you can see that all the arrows I'm drawing now are left and right, and you can just say all the arrows that point left in the direction of acceleration are positive, all the ones pointing to the right are negative. So that's one strategy we'll use, is to kind of get rid of these pulleys right here and straighten out the problem. And they're able to visualize it and think through it and analyze it more clearly. So if that helps you, fantastic. If it makes no sense to you at all, ignore that. Don't ever use it. Okay? Let's just take one more glance at the assignment, make sure we haven't left anything totally undone here. I think the hardest problem is done for you now. There are some other problems here, but that one's not too bad. For this one, you will need to think about the fact that they give you the distance of 5 meters and how you can use that to help you find an acceleration, because you can. Okay, so that 5 meters can help you find that. Let's see. This problem is not terribly different than the one we just worked. All of the forces are in a beautiful, perfect straight line. So each of these 2 objects here is going to have some kind of weight parallel component going down. This is simpler in that there's no friction. Okay, friction is 0 here, but you are going to have weight going down. You'll have tensions going up. They're going to ask you some questions about that. This one is similar to something we mentioned already, okay, where the F is the biggest tension because to pull all 3. But I don't want to do that for you. Again, the surface is frictionless, which makes the problem just kind of reduced, kind of simpler, less terms. So that is easier to work with. I think we've done enough that you should be able to work the rest of it on your own here, or at least get a lot of it done. So have fun, and let me know if you have any trouble with this, and I will be happy to answer any questions via email or when I see you in class.